Welcome back to this class. Today we'll be discussing stability of incrementally raised embankments. Last time we saw the layout and the water balance and the critical conditions for stability. This time we'll go a little more into depth into the stability of embankments. But before we start that, there was one small topic which has overflown, and that is about the decanting arrangement. Now, we talked last time that the location of the phreatic line is very important. We talked that the location of the phreatic line is very important. Keep the ponded level as low, and then the phreatic line will be low and the stability will be higher. But if the ponded level is high, you have a problem. So let's look at this. I'm just looking at the inflow. So I'm throwing in my slurry into a ring impoundment, and I want to take out the supernatant water, or the water which is at the top after the solids have settled down. So give me an arrangement. How will you do that? How will you take out the water from the top, the clear water from the top? When it's coming in, it's in the form of a slurry, and how will you take out the clear water from the top? We can have a spillway, we can have a trench, we can have something to pump it out. These are some of the options. But we don't want the phreatic line to be high. See, one of the ways I can say is, let me put an overflow weir here. Just a thought. Let me put an overflow weir here, like a spillway, and when the water level comes, I can have an energy dissipator, and I'll allow the water to overflow. But that means I'm going to allow the water to reach the crest of the spillway, right? That means I'm increasing the water level. The fact of the matter is, I could have, if at the moment my deposited slurry was at this level and the decanting, the supernatant fluid was here, I could have, so this is what the material which got deposited. Let us say this is 6 meters and this is deposited material is 2 meters, and I have half a meter of water on top. I should have removed this water. If I had removed the water, the phreatic line would have been low. But we want to operate it like a lake. So I allow the water to fill, and more water to fill, and more water to fill. What happens? Phreatic line rises. So I need a decanting arrangement which allows the water to come out as the ash settles and the clear water moves up. That's the criticality of design. Otherwise, I can always make a well, right? So that just like you have the overflow weir, I can make a well that when the water is at this level, it will flow into this and go out. But all these wells with water inflowing from the top, or the weirs with the water overflowing from the top, they make the water level go up. I actually need something which is moving. Moving means as the ash fills up, I allow the water to come out. When the ash rises, I move it up. Think it's possible? Let's see. How do we decant? Because decanting is critical to low phreatic line. You agree? If I can decant quickly and properly, my phreatic line will remain depressed. So pumps or siphons mounted on floating barges are often used for decanting of ponded water. You should have said, sir, I'll keep a boat. I'll have a pump and a pipe. Wherever I see water, I'll start sucking it out. Right? All you'll have to do is that the boat doesn't run aground. But even if it does run aground, you won't be lost. You can still reach the end. So in India, this is not used. In some of the developed worlds, this is used. And I'll come back to why. So what we use are basically water escape towers. These are vertical concrete wells or risers with intake ports that extend from the bottom upwards to the ash deposit. Overflow weirs have been reported sometimes in the past, but not very successful. So the biggest company which handles ash ponds and therefore a large number of slurry ponds, maybe 60, 70 slurry ponds in India, is National Thermal Power Corporation. So they tend to use this water escape towers called decant towers. And the idea is that the water is allowed to spill over the periphery of the water escape tower into the tower, and this level is adjustable with some kind of precast slabs or holes. I'll show you. If I have a well or a decant tower which has several holes, okay? Now, when I am depositing the slurry here, this hole is open. So the water will go through from here. Now the ash has reached this level. I'll close this port. I'll seal it with cement, concrete. And then I allow the slurry to deposit more, then the water is overflowing from here. So the water never comes to the top. As long as the deposited slurry level is low, the level of the well is above the deposited slurry level, but is not at the crest of the dam. So at the moment what you are seeing is that, so when was slurry had deposited up to this level, this port was open. Now the slurry has deposited up to this level, this port is open, these are all closed. So the supernatant water will fall through this, go into the well and go through the dam out. And when the slurry level rises, this port will be closed. When the next embankment will be made, then the ports will go higher and higher. When the third embankment will be made, what will happen? It will sit on top of the well. So your well has to be sufficiently back in your design. If you are going to have 6 raisings, you can't have a well which comes under the footprint of the perimeter embankment after the second raising. And that was something also which was developed from time to time as we went along. So this is the concept of a barge with a pump, that you have a barge which floats around, you have a pump which sucks out the water, and it goes out through a pipe. The difference between the two is this requires no electricity. Water flow is through gravity. This requires electricity. It requires power. It requires a human being to be around to operate it, operate the barge and operate the pump. Whereas here you can open a port and go away and come back. You know that the slurry level is going to rise after 2 days or 3 days of a week or month. Then you come back and close it and open the other port. So these are called fixed location decant towers. These are called mobile barges. And you can see 2 arrangements here. If this is a side hill impoundment, this is the embankment. There can be a decant tower here, inflow pipeline here. The port is open at this level and the water is flowing out. In the case of a floating barge, your inflow can be here, water will assemble here and you can pump it out. Now I want you to focus on one aspect which we will discuss as we go along. Where are the fines getting deposited here and where are the fines getting deposited? See, there's the coarse tailings and the fine tailings, or the coarse ash and the fine ash. In this condition, where is the fine ash or fine tailings getting deposited? Here or here? Near the decant tower. The outflow zone has the fines. So remember, when you are going to raise this, you are going to have fines underneath. What's happening here? The coarse material is depositing here and the fines will come here. So the issue always is that you should have coarser material near your embankments and not finer. So wherever the decant tower is close to the embankment, that portion becomes problematic. You know, you have a ring. I just showed you a huge ring impoundment. In the ring, the decant tower was at one end. So at the other ends, there was garland inflow. So that is not a problem because this is the beach. This is called the beach and this is called the ponded area. The beach always has the coarser material. So in all the places where the inflow pipes are on the garland arrangement, they are getting a beach, they are having the coarser material. But wherever there is the well, there is the finer material, and there you have to be careful. Water is high, fines have been deposited, strength is low, material is loose. So this is the typical design of an NTPC water escape structure. Please note this is vertically exaggerated. This is a dike. It is their drawing, not mine. This dike slope looks like concrete dike. It's not. It's a soil dike or an ash dike. So it will be like that. So this first raise is starter, first raising, second raising. Okay. So they keep the water escape structure far away, and you have an access bridge to it, such that at least for 5 raisings it does not get submerged. They don't have ports. These are hexagonal in shape, so this is one water escape structure. Okay. They have these precast slabs which can go down grooves. I'll come back. So the precast slabs are being placed. They're continuously being raised in increments. And when you put the precast slab, you send somebody in to seal the joints. So when the slurry is at this level, water is overflowing from here, then they put the first slab, then the second slab, and it keeps on going higher and higher like that. So this is the water escape structure used by NTPC, and this is the dike. So below it the water escape pipeline is placed. These are twin structures that have been shown. So these are the precast panels which just keep on raising the weir height. So the advantages and disadvantages: decant towers are fixed in position. Water is somewhere else and the tower is somewhere else. It can happen, don't worry. Why? Water will go where it wants to go, depending on the slope of how it got deposited. So barge will go after the water. Of course, unless it is marooned in one corner, in which case also you can get a light barge and pick it up and take it there. So they are fixed in position and they need regular adjustment of the port openings. They require a conduit through the embankment. Now, when we teach earth and rock-filled dams or earth dams, we normally say avoid a rigid element within the embankment. Why? Differential settlements are an issue. This conduit may develop a crack. If it develops a crack, the fines will go through it. And then, just like we had a photograph today morning, you didn't discuss it. Have you seen the papers? Yes. What happened? What happened? In Chennai, something happened. I don't know. All I saw was a bus had fallen into a cavity. So there's a road and the bus is traveling and suddenly there's a gaping cavity. Obviously underground something happened, whether it was a tunnel or whether it was a collapse of a sewer pipeline. Typically what happens that buried pipelines in a long-term perspective of 50 to 100 years would have some kind of problems associated with them. So we avoid it. But at the moment we are putting conduits. These are not permanent lakes. Eventually the pond will become full. After the pond will become full, the slurry won't come. There will be no water escaping. So it is not like a lake or a dam where water is escaping all the time. Decant barges, they are flexible and can be moved. There is no conduit through the base of the dam, so they look very good, but they require pumping. And thus they need power. So in India, we are still using decant towers. In the old ponds, we had overflow weirs. What is the problem with overflow weirs? As you go up by the upstream method, what happens to the overflow weir? You can make the overflow weir for the first case. Overflow weir will be like a concrete structure with water overflowing it. Now you've moved it back. Well, you can put your overflow weir back, but the overflow weir will be resting on loose deposited tailings or ash. So that will start to have differential cracking. So you can't make a rigid structure and put it on loose hydraulically deposited material. So overflow weirs are virtually out. And many a times this problem has been referred to IITs, and we have been asked, can we put a filter embankment? That means let us have a flexible system. What's a flexible system? I have a ring impoundment. and this is my embankment. Let's make this portion a porous embankment. Porous embankment means which allows drainage. Water to flow through it, does not allow the ash or the tailings to come out. And see what happens. One can always say, all right, would you like to make a porous embankment? What will you make it of? If I ask you to make a porous embankment, what would you make it of? Cross section. Very, very porous. Gravel, very good. Even you have bothered that gravel may get washed out. What's the next step? No, cobbles. Let's go to cobbles. Cobbles don't get washed out. In rivers, cobbles also come down the river in the monsoons. You're aware that when the rivers come out of hills, if you stand on a bridge, in the monsoons you can hear the big, big cobbles hitting your piers. Dum, dum. You should go to a bridge which is just downstream of a mountain range, coming out into the plains. These are rolling down like a debris flow. Anyways, so we're getting diverted. So I would like to make my porous embankment of cobbles. I don't want cobbles or boulders. You have done rock-filled dams. You have earth dams. You have earth-cum rock-filled dams, and you have rock-filled dams. Heard about them? Anyways, read up about them. These are dams which allow water to go through them, over them, but they are made of rock fill. So, sounds good? Now, what's the problem? If you make it of cobbles, your ash slurry will also come out of it. And what else? Mine tailings will also come out of it because it will have large, large holes in it. So, what will you do? You will now make a filter. The material which is coming is ash slurry, fines. What is the fines? What is the grain size distribution of? No, total material is silty sand. Towards the inflow is here, outflow is here. What's the material coming in? More silt. So you need a filter between a silt and cobble. Oh, that's a lot of filters. Immediately, how many number of filters do you think you would like to put? Behind the cobble will be gravel. Behind the gravel will be coarse sand. Behind the coarse sand will be fine sand. Behind the fine sand will be silt. So at least 4 layers. You'll have to apply the filter criteria of the Zagi. We all aware of that, D15 and D85 ratios, the 2 ones. So basically what you're going to do then is to put layers. Looks good? Should work? Better than your well. You don't have to wake up in the middle of the night and say, oh, I had to close this port. Because if you forget to close the port, what will happen? Fines will come, and the next morning, knock, 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 Central Pollution Control Board, people will be at your office and say, here, look, white water coming, ashy water. He says, I was sleeping. So that is not an explanation, and if it is America, you'll be behind bars. Yeah, in America, they punish you for all the wrong, and therefore you do all things right. Here we say, all right, कोई बात नहीं, 6 घंटे का penalty ले लो, अभी हम जाके port, we are closing the port. Anyway, so I have now gravel, coarse sand. I'm just putting, please, I don't know whether this is, assuming that I'm trying to stop fine silt from coming in. I just put silt and then your slurry will come in here. Looks very exciting. This is the solution which we should have. There are 2 problems here. One problem is, what is the upstream slope now made of? What is this upstream slope made of? What is the problem with silt? Firstly, you don't get pure silt. Secondly, erosion again starts to give you dust. It starts to get wind, gullies. So you come to a designer like Manoj Datta and he will say, okay, let's stop this dusting from taking place. Let's make yet another filter. Sand, gravel. How do you like it? Any problems? This is the correct way of having an upstream slope which does not erode and still has a silt barrier inside which will not allow the fine particles to go through it. Does it look sensible or no? It's very expensive now. The expenses are going up. Anybody would like to punch a hole through this? So that's my slurry carrying the fines. The coarse particles have all settled. So what will happen? These fines will start to come in. They can't pass through. Water will pass through and fines will not pass through. Agreed? Is it a good filter? Absolutely, absolutely. Once your fines start to settle, it will start to clog up your drain. You must have the capacity that what is inflowing must flow out, otherwise the water level will rise. So suppose it chokes it, you will say, so what? At least the fines are not going up. Then your water level is rising, and finally what will happen? Water will start flowing over from the top, and again the fines will come out. So flexible filters have not really worked. We've tried it at 2 locations. They worked for a few years and then they started to choke. And now let's go back to the bag filter, where we are using bag filters to entrap fly ash. You have electrostatic precipitators, or you can also have bag filters for fine dust collection in various. What happens to a bag filter? In a bag filter, through the geotextile, the dust plus air goes through, and dust settles and entraps in the bag filter. After some time, the bag gets choked. Then what do? We can replace it or we can unchoke it. How do you unchoke it? Well, either you backflush or you take some kind of mechanical devices and bang up the bags or vibrate the bags so that if there is any material which has formed a thin film on it, it falls down. So you have to have a mechanism for unchoking. Where is my choking occurring here? Is it occurring at this gravel, sand or silt or fine sand? Or what is getting choked? Where are the fines? Where is a layer of fines formed? No. The fine silt comes and is held by the silt here. This silt. It will allow the water particles to go through, but it will not allow the fine silt part. So the fine silt particles come and form a thin film on the silt. Can I unchoke it? We don't have an arrangement. However, if instead of all this I was to make this whole arrangement but have a geotextile filter, if I was to have a geotextile filter, then I could replace the geotextile filter. That's what we are doing in a bag filter. The only thing is that the geotextile filter is progressively getting buried in the slurry which is deposited. Can you see the engineering here? You can come and say, sir, I don't agree with you. I will have cobbles, I'll have gravel, I will have coarse sand, I'll have fine sand. Instead of the silt, I'll put a geotextile filter. Right? And I will give you a geotextile filter which can remain exposed for the 5 years. Or if you are bothered about it, okay, on the geotextile filter you put some cobbles so that your geotextile filter is protected from animals, from man, from vandalizing. Right? So your silt particles will now come and sit on front of the geotextile filter. Now you want to replace it. Now you know it's not working, you want to replace it. The problem is it gets buried because the ash level or the tailings level is rising. So we need to have a chamber which is so designed where this filter can be changed with time. And so far, it's not been developed. So if any of you want to do it, you can always make a design, you can patent it, you can have a startup, and you can make millions of dollars. Does it excite you? Great, I hope one of you will do this. But it's all there. Conceptually, it is possible, it is doable, but just a filter embankment does not work. So what is this diagram which I have put here? I said cobbles, gravel, coarse sand, fine sand. And on top of that, there is a dash, dash, dash line. That is what you're going to develop. That's your patented. So I've said it is a protective porous layer which will allow the water to go through but keep the fine ash in position. However, you also have to have a mechanism by which this can be replaced periodically. And this is better than all the other water treatment techniques which are being used, which is what? If you want to remove a lot of fine suspended solids in water treatment, how do you remove them? No. You are drinking water plant. You have picked up water from the river, total suspended solids are high. What will you do? Sedimentation, you'll have to make a lake. Rapid sand filter. Rapid sand filter catches the suspended solids or catches something else? Everything. And what happens to rapid sand filter after a month? And what do you do to that? And then what happens? It clogs faster, because when you backflush it, you don't take everything away. You have to change the rapid sand filter. Inevitably, please understand, this problem would then become one in which you should be able to remove the fines which are clogging, or change the geotextile filter and put a new one, or take it away and wash it and put it back again. After all, clogging is a reversible phenomenon. It's a reversible mechanical phenomenon. You can backwash it with water or you can backwash it with air. So much potential. That's why I left the word conceptual, that one of you, within the next 10 years, I'll see your name in the papers that you developed such a lovely concept for the various slurry ponds. And believe me, every slurry pond, when there are high inflows and the pond is almost full, that means settlement time is not large, has a tendency to send out some milky effluent sometimes, because it's an open system, it's not a closed. The other way to do it is to put coagulants in it. You have a lot of suspended solids, you put coagulants so that they all coagulate and they, but look at the amount of chemical being used. Look at the amount of agent being used for the purpose of coagulation. And then the coagulated particles themselves become contaminated particle. Why? Because they are coagulating around a chemical which is not supposed to be there in the environment. So this is one of the more critical designs. It's not a geotechnical issue, but if you go towards a filter embankment, then it's a geotechnical design. And it's a design which is well within your realm of being able to solve. Any questions, any thoughts? I see a lot of excitement. I'm encouraged. Let's get back to the stability of incrementally raised embankments. So if you have got a good decanting system, your phreatic line will remain low. That's what I'm saying. Because any system which will allow clear water to come out and not allow water to accumulate in the pond is what we need. At the moment, because the water doesn't become clear, the operator keeps on holding the water. It will settle, it will settle. The more you hold the water, the more the pond rises. Because the power plant can't stop and the mill which is producing the tailings can't stop. They work 24/7. So, and as it rises, phreatic line rises. So, as we said, we have raising by the upstream method, the downstream and the centerline method. When you do downstream and centerline method, we have well compacted strong material. When you have upstream method, you have the problem that you are putting each embankment on slurry deposited loose material. And just quickly recall this. These are the type of failure surfaces that you will get. And in India, as I said, most of the dikes are being raised by the upstream method of construction. It's because it's more economical and you started at the outer, it's very nice to say, let's start inside and we'll do downstream method of construction. Now, if there is any population around, the tendency is to encroach the land. So you started inside, but people came and started living around it. Then you can't get the land to do your downstream construction. So if you ask a thermal power station or a mine people, he says, no, first we have to make the embankment at the periphery and put the water inside. Why? Then nobody will come and live inside or outside. If you make the perimeter and don't put water inside, still they will come and live. So at one place, they said, all right, we will do downstream method of construction, but let's make a ring bund at the outside and let's start the construction on the inside. And we'll come from the inside to the outside. But what happened? You only had to walk over a small bund of 2 meters. So if you could encroach flat ground, you could encroach this. And please understand, these are not military installations, you know. You're not having people standing around, people preventing people from squatting. You can't. Your own construction labor, your own people start to, you know, take over. So we now come to the stability of this incrementally raised embankment, and this is a concept which I discussed last time also, the concept of an infinite slope to a finite slope. Don't mind this little aberration, you know, this should also be a part of this circle. But I made it so that you are able to see it and say, sir, something is wrong in the drawing. The thing which is wrong in the drawing and why I made it like this was, is this a finite slope or an infinite slope? Please tell me. This one. It is horizontal at the top, horizontal at the bottom. Is it a finite slope or infinite slope? Finite, okay. This is about 5 kilometers long. Is it finite or infinite? We discussed this, I think, briefly. When the failure surface does not see the two ends, this or this. You know, if this is 5 kilometers long, this thickness must be 2 kilometers. There is no such failure surface which exists. So when the failure surface is a few meters and the slope is a few hundred meters, then it won't see the ends. So this is like an infinite slope analysis. Whether the circle is here or whether the circle is here, as long as these two ends don't come into play, it becomes like a infinite slope analysis. Should we discuss this a little more? It's fundamental to understanding the concept of infinite slope. Two slopes, identical angles, identical diagrams on this blackboard. One is 5 kilometers, or not say one. Let's say one is 1 kilometer long and one is 20 meters long. Only difference is in scale. That's about it, right? And if I have this failure surface, or I have this failure surface, or I have this failure surface, or I have this failure surface, as long as the strength of the material inside is the same, all of them are going to give you the same factors of safety. Agreed? Because they don't see the ends. As far as this failure surface is concerned, W, what is the downward angle? W cos alpha? W sine is downward, W cos is normal, right. So W cos tan phi is the resistance and W sine beta or whatever is the driving. So all of them have identical values as long as the strength parameters are a constant. So this is infinite slope for these failure surfaces. Whether this exists or whether it exists here or whether it exists there, it doesn't matter. However, if this is 10 meters high and my failure surface is like this, now when I move this failure surface, the factor of safety changes. Why? Because the end effects are in play. I bring this failure surface here, now it's a different factor of safety. This is a finite slope. And whether it is infinite or finite depends on the depth or the thickness of the failure zone with respect to the height of the slope. So typically hill slopes, I told you, typically hill slopes may be 100 meters or more, but there will be a rock somewhere beneath it, and therefore all your failures will be infinite slope failures because this can't go into the rock. Whereas another hill slope, another soil slope of the Ramganga Dam, how high is it? Tehri Dam?
220 meters.
I think it's more than 220 meters. Anyways, let's take an earth dam, earth cum rock fill dam more than 200 meters high. This is this. But here, the failure surface can go through the foundation also, depending on whether it's on a soft foundation. So when the thickness or the depth of the failure surface is comparable to the height of the slope, then you are having a finite slope. This is important for you to understand. Infinite slopes and finite slopes. Because once you have infinite slope, you have some simple formulae to deal with. When you have infinite slope, you have some simple formulae. When you have finite slopes, you have more complex formulae to deal with. So therefore, when you do landslide analysis, or when you are doing analysis of hill slopes where the rock is there at 2 or 3 meters depth, then the superficial failure surfaces are only 2 to 3 meters deep and the hill is 100 meters high. Then you have an infinite slope analysis. Whereas an earth dam of 100 meters high, which has no rock above or below, is going to be a finite slope analysis. So when you have infinite slope analysis, just for simplification of things, in cohesionless soil, because for us ash and tailings are cohesionless, C dash is 0, then so nice equation comes. Factor of safety is equal to tan phi dash by tan beta. Is this developed, is this equation for a circular failure surface or a straight line failure surface? Straight line failure surface parallel to the outer slope. You remember? So is that valid? I am showing you circular, and here I am talking of formula which are. So when I increase the radius very high, I just want to finish this issue that this is my limited depth to which the failure can take place. I can put my center of rotation very far. When I put my center of rotation very far, then it's almost failure surface parallel to the outer slope. These two edges are too small and it's almost like. So in a sense, for infinite slopes in cohesionless materials, you can use this formula and say this is the formula for a circular failure surface with infinite radius. A circular failure surface with infinite radius will be a straight line? Perhaps. So I have this, and when flow occurs parallel to the slope, I have this. Agreed? We've done this, flow occurs parallel to the slope. Flow occurs to the parallel to the slope is the same as submerged slope. Let me say, this is factor of safety for infinite dry slope. Now if I have infinite submerged slope, what's the factor of safety? Is it this or is it this? Yeah, whether it is submerged or whether it is dry, the formula is the same. Maybe under the submerged condition phi dash will change. But do remember, only when flow is occurring parallel to the outer slope does this come into account. So again, I want to clarify this concept that I have dry slope, I have dry submerged slope. That means water is there on this side and water is there on the inside and everything is submerged but there is no flow. And I have dry slope in which water is flowing like this. So in these two cases, this is submerged, this is flow. In these two cases, it's tan phi dash by tan beta. It's possible that the submerged soil may have a different phi dash by a few degrees. If it's in sand, sometimes phi dash dry may be 35 and phi dash saturated may be 32, 33. Not necessarily, so sometimes they are identical. But that is on accrual on the difference in the phi dash. Here, the factor of safety becomes gamma b by gamma t. So these are the formulae which we use for the purpose of understanding infinite slopes. When we apply them to ponds, I just want to bring that photograph. When we apply them to ponds which are finite slopes, I will look at dry slope. I will look at a dry slope with no internal drain, then the phreatic surface will be like this. Here you will see its flow acting downwards. I'll have a formula for this and I'll have a formula for this. And when I put internal drains, this phreatic surface will go backwards. So do remember that our factor of safety is between the dry case and the flow parallel case. And the further away I can take this phreatic line from the downstream surface, the better is my factor of safety. Right? And we'll stop this discussion here today. But all I've been trying to tell you is, the further you keep the phreatic surface, the lower you keep the phreatic line, the better the stability. The higher the ponded level, the closer the phreatic surface. Between downstream method of construction and upstream method of construction, which has a phreatic line which is higher. Both have got internal drains, which will have a phreatic line which is closer to the outer surface. Let's just look at it. This is my upstream method of construction, right? And my water is full here, it will come like this. Very close to the outer surface. This is my downstream method of construction, and my drain is like this and water is being taken out. So whenever the water comes, it is caught by this drain. So it's far away from the downstream slope. So in downstream method of construction, the phreatic line is far away. In the upstream method of construction, you can make a very nice chimney drain, but the phreatic line is still pretty close to the downstream phase. So this factor of safety is not as high as in the downstream phase. We'll stop here today, and we'll take up this discussion in more detail in the next class. Any questions which come to your mind, which you feel which you feel to discuss, and also the fact that are you going to develop the next decanting arrangement, 2G, 3G, 4G. So we started with the weir 1G, then we came to the tower 2G, then we came to the barge 3G. We are looking for some 4G, 5G solutions. Anybody up to the task? I leave the thought with you. We'll take up this discussion in the next class. All the best.